So assume that f and g are differentiable and the derivative of g is not equal to 0 near A. Okay, so these are our assumptions. Assume we have given two functions, f and g, which are differentiable. The derivative of g is not equal to 0 near A, but it's not necessary that f and g and the derivative of g are defined at A, so this is not really necessary for the result. Furthermore, assume that either the limit of f of x as x tends to A is equal to the limit of g of x as x tends to A is equal to 0. Or you have the same with infinities, or also the case where both limits are equal to either plus or minus infinity are covered by this theorem. But I do not have too much space, so I'm not going to write down this case. We're just considering this case for the proof. Then the limit f of x over g of x. Okay, so we are not able to compute this limit by the usual limit laws, because if you just apply the limit laws, you will get 0 over 0. And we saw already via examples that 0 over 0 can take on. So this situation can take on any value, any possible real number. But the theorem of the L'Hopital tells us a convenient way how to compute this limit. Namely, you take derivatives of a numerator and denominator and compute the corresponding limits. And those two limits have to be equal if this limit exists here. If the later limit exists. Okay, so last time I gave you also an intuitive explanation why this result is true. Maybe I recall this once more, because actually this intuitive interpretation is quite important. For instance, we have the situation where the functions f and g are like this. So this is the function g of x. This is the function f of x. Okay, you see that we are in this case, okay, where the limits so you can think about this condition as f of a and g of a is equal to 0, but it's not necessary that f and g are defined at a or continuous at a. But if we look at this situation, then you see, okay, as you zoom in, as x is getting closer and closer to a, okay, the two functions should look more and more like the tangents. Okay, so you have here a tangent to the function f of x at the point a, and you have a tangent to the function g of x at a. And if you want to compute the limit x tends to a, f of x over g of x, okay, so this should be roughly similar to the limit where the two functions are replaced by the tangents. And in this situation, the tangent to f at the point a is given like this here, over the tangent to g at a. Okay, now you can see, okay, that if you look at things like this, you can erase the bad guy here, and what remains is just this limit here. Okay. Of course, here this situation is simplified. Namely, I assume that the function f and g are both defined at a, and so on. But it roughly explains, okay, why those two limits should be equal. Okay, this is not a proof. Now, last time I showed you already that if you use stronger assumptions, namely, if you assume in addition that the two functions f and g are not only differentiable, but also the derivatives are also continuous, and you assume that this property does not only hold for x close to a, but for all x, also including a, okay, so for all x in the interval containing a, then we saw that under those stronger assumptions, the proof of this theorem is very easy. Okay, but here we do not necessarily need that the derivatives of f and g are continuous. Actually, to find a function where the derivative exists but is not continuous, it's not so easy. Maybe I will say a little bit about this in half an hour. But let's first maybe look at the proof of this result here. So maybe this is the most important thing you should remember, because in particular high school students tend to think that this theorem is quite mysterious, because it connects, it is not clear at all for them. Why should there be a connection between those two limits? So if you have learned in high school, of course you haven't proved the result, but maybe you saw in high school that the theorem is quite mysterious, connecting those two seemingly unconnected limits. But if you look at this heuristic, this explains pretty well why this theorem should hold, and why indeed there is a relation between those two limits. Under special assumptions for f and g, smooth enough. So maybe that's the most important thing you should understand. If you look at the proof, maybe the proof contains too many details, and you do not get a clear feeling why those two limits are, must be the same. So how to prove this result? Now, we see that by assumption this limit, so our assumptions are that f and g are differentiable, the derivative of g is not equal to 0, and that this limit here exists. Okay, this is also an assumption. Okay, so we know that this limit here exists, so let's call it L. It's the limit x tends to a of the derivatives. We will see in a few minutes by looking at examples that actually this assumption here, that the limit exists, is important. If the limit does not exist, and here in existence of limits we include the cases plus minus infinity. So if the limit is equal to plus or minus infinity, we still say that the limit exists. Okay, actually it doesn't exist, but in a special way. So for the moment we include in our notation of existence of the limit also the cases plus minus infinity. In all those cases, those two limits must be the same. Okay, but if this limit does not exist, okay, it's not necessary that this limit does not exist. Okay, it's not necessary that you can conclude back. So actually, this is an important assumption that this limit here exists. Okay, so our aim is to prove that this limit here is equal to this limit. Now, for this, we need again a connection between the original function and the derivative. We know such a connection, strong connection, is provided by the mean value theorem. Now, we will apply the mean value theorem also here in this situation. We will define. So, first assume that, just for convenience, assume that x is larger than a. Okay, so we are just to the right of a. Now, we are going to define two new functions. The first one we call large capital F of x. Now, the definition is almost the same as f of x. So actually, this function will be f of x if x is larger than a, and in case where x is equal to a. So for x is equal to a, the function f is not necessarily defined, okay, by those assumptions here, but we can set it to 0 in order to make this function here continuous. Okay, and we give a similar definition, g of x, capital G of x, where we replace f by g. Now I do not have too much. Actually, I don't want to erase this result, but since I do not have too much space, I have to do it. Okay, so we define another function, g of x, which is g of x if x is larger than a, and 0 if x is equal to a. Okay. Now, what have we gained? So, observe that both f of x and g of x are continuous on the whole interval from a to x. Okay. Closed. Okay. So the important thing why we define for x is equal to a the function like this is that at the left boundary, okay, the function f and g are continuous as well. The function is clearly continuous if we stay away from the boundary because it's differentiable. Okay. Moreover, the assumption tells us that f of x and g of x are differentiable on the open interval ax. So x must be close enough to a, okay, in order to ensure this. Okay. Moreover, if you look at the derivative of both are just equal of capital F and capital G are just equal to the derivative of small f and small g. Okay, inside this interval, because there the functions coincide with the functions small f and small g. Okay, you also observe that if you look at the derivative of g of x, okay, so actually nothing else but this derivative. Okay, now because of assumption again is not equal to 0. Okay, actually if, for all now I'm choose here. It's a little bit awkward that this point is also called x here, so maybe let's call this point x0 just to make this more clearer. So here this point is x0, this point is x0. So this holds also this holds for all x in this interval here. These are just the assumptions, okay? And now if you think back, we have learned another version of the mean value theorem, which is due to Cauchy's mean value theorem, which just applies under such a situation where you have two functions which are continuous on a closed interval, which are differentiable on the corresponding open interval, and one of the functions has the property that the derivative is not equal to 0 for all x in the closed interval. So we know from Cauchy's mean value theorem that there must exist some c inside this interval here, or call this y, inside the interval ax0, okay, such that the derivative of g of y over the derivative of f of y is equal to g of x0 minus g of a over f of x0. The other way around, sorry. G and f. G of x0 minus g of a. Okay, so here I use Cauchy's mean value theorem, not the usual mean value theorem. And now you see from this, our conclusion almost follows. Okay, so because here the y is inside this interval here, okay, so actually the derivative of capital F is equal to the derivative of small f, and the derivative of capital G is equal to the derivative of small g. Moreover, you observe that by definition, f of a and g of a are both equal to 0. Okay, so you see that this actually tells you that the derivative of small f at y over the derivative of small g at y must be equal to f of x0 over g of x0. And now let x0, okay, tend to a, and we are moving from we are approaching a from the right. Okay, so you see that the limit as x approaches x0 from a from the right, okay. So is let's call it x0. So is f of x0 over g of x0 must be equal to the limit x0 approaches a from the right, the derivative of f at y over the derivative of g at y. Now you see if as x0 is moving to a, okay, the y is moving to a as well, okay, because the y is between a and x0. So this means that actually you can replace here the x0 tends to the x0 by the y, but this limit here by assumption exists, okay, and is equal to L. So now we have already proved that the right-hand limit, okay, of this quantity exists and is equal to L, and we do the same for the left-hand limit, which then tells us, okay, that indeed the limit of f of x over g of x as x approaches a exists and is equal to the limit of the derivatives. So this just follows by another application of the mean value theorem, which is not a surprise because the rules of the L'Hopital tell you that there is a relationship between the limit, the original limit, and the limit of the derivatives. And our main tool for proving such results concerning a relationship between the derivatives and the original functions was always the mean value theorem. Okay, so any questions to this? Observe, this doesn't prove everything. Because I told you that if, for instance, if this limit, okay, does not exist but is equal to plus infinity, the result holds as well. Okay, you have to adjust the proof a little bit, okay, for this situation. Also, if you replace the limit here by, if you replace in the rules of the L'Hopital limits by right-hand limits or left-hand limits, the result is still true. Okay, you just have to modify suitably the assumptions, and you have to modify the proof. Moreover, the rules of the L'Hopital still hold for limits at infinity. So if a is equal to infinity, the same result holds. Okay, but of course you cannot use this proof here because you cannot define the function equal to 0 if x is equal to infinity. This doesn't make sense. Okay, so if a is equal to infinity, okay, you have to use a different way to prove this. Okay, but actually, if a is equal to infinity, okay, then you replace x by 1 minus x. Okay, and then you just use what we have proved. Okay. So actually, all other cases, I think in our textbook also some other cases are discussed. Not all cases, but all other cases you can actually relate to the case which I have just proved. Okay, and the result also holds if the limits of f of x and g of x are equal to infinity, not equal to 0 at a. Okay. Also for this situation, you cannot use the same proof because if the limit of f of x as x tends to a is equal to infinity, of course you cannot define here infinity if x is equal to a. Okay, it doesn't make sense, but also this situation is easily handled. You just replace the original function by 1 over f of x and 1 over g of x and use this proof here. Okay, so that's the way the rules of the L'Hopital are proved. Are there any questions to this? Now, maybe let's look at some examples. As I said, it's not really necessary if you completely understand all details here. Some students might be more interested into applying the results. This is just for students who are more interested in the theory. But what you should at least understand is this heuristic argument which I showed you, which explains that what the rules of the L'Hopital tells you, okay, is not a surprise. It's something which is quite expected. Okay, yesterday I already stated some examples like ln x over x minus 1, and the limit x tends to 1. So this can now be easily handled. You just have to take derivatives. You have to check always. You have to be careful that the assumptions are satisfied, which means, okay, you have to check whether you are actually encountering a situation where you have 0 over 0 or infinity over infinity. If you do not encounter such a situation, and you still, so if you could compute the limit already now by using limit laws, and you still use the rules of the L'Hopital, it's not necessarily true that there is a relation between this limit and the limit of the derivatives. They can be different. Okay, so you have to make sure that the assumptions are satisfied. Here they are satisfied, 0 over 0. Okay, so we just use the theorem. So the derivative of the numerator is 1 over x. The derivative of the denominator is equal to 1, and now you can easily compute the limit, which is equal to 1. So you see that actually the way you use the rules of the L'Hopital is, okay, because this limit here exists, okay? So first you try, and then if this limit exists, you can conclude back. Okay? So you have to check whether the last limit exists or not. And it's kind of like we applied the racetrack principle, okay? You first have to check whether certain assumptions are satisfied, okay? And then you can conclude back. Now, if you have the similar situation where x tends to infinity, okay, also in this case, as I said, the rules of the L'Hopital are still, you can still apply them, so you have infinity over infinity, so you have the limit as x tends to infinity, 1 over x, which is equal to 0 in this case. This is not a surprise, because we know that the logarithmic function, ln of x, will grow slower than every power function. Okay, so since this means, okay, that you are now interested, you have the indeterminate forms, infinity over infinity, okay, and the behavior is determined by the function which grows faster to infinity. Okay, but we know that this function x here grows much faster to infinity as ln of x. So it's expected that the limit is equal to 0. In particular, if you replace here x by any power function, okay, so for instance, x to the square, square root of x, or x to the 1 over 1,000, the 1,000th root of x, okay, the limit will still be equal to 0, okay, because no matter, if you replace this by x to the alpha larger than 0, okay, this function will always grow faster than ln of x. And actually, you can use the rules of the L'Hopital in order to prove this. Now, another simple example is the following one. Okay, so for this limits, again, without using the rules, we know that the exponential function is growing faster than every power function, so the limit should be equal to infinity. Now, you see that we indeed have infinity over infinity if we just intend to use the limit laws. So this is a situation where we can apply the rules of the L'Hopital. Now, if you apply it once, you see that what you get is e to the x over 2x, but you still encounter the situation infinity over infinity. Okay, so you have to do it once more. And now what you get is e to the x half, and this is indeed equal to infinity. Okay, I know this example is very easy, but you should, from this example, you should understand that actually the first few steps here are in question. Okay, we are not sure whether we are allowed to apply here the rules of the L'Hopital, because we know that one assumption in the rules of the L'Hopital are that this limit here exists. Okay, so here, if we use here the rules of the L'Hopital, okay, we are not finished because we do not know whether this limit exists here. Okay, so actually we are not sure whether we are allowed to do whether those two are really equal. Okay, because we do not know whether the limit exists. So we use them once more. Okay, now we see, okay, this limit exists. Okay, so the existence, as I have explained, includes the case plus infinity. Okay, so here the limit exists. Now we can conclude back. Okay, so this means those two are equal. In particular, this limit is also infinity. And now we can conclude once more back and say, okay, this means that those two are equal. Okay, so actually you first try and then you work back from behind, logically. this is sometimes, this remark seems to be trivial. Maybe this is something you have not, which was not emphasized in high school, but which is rather essential, because if you look, for instance, this example. This one. Okay, so we observe that if you use the rules of the if you want to use the limit laws, we observe that the function is what we have is infinity over infinity. Okay, because it doesn't make a big difference for the growth of x squared. Okay, because this is larger equal than -1, smaller equal than 1. Okay, so still this function will tend to infinity. So we have infinity over infinity. Okay, so we can use the rules of the L'Hopital, or we can try to use them. We see that, okay, the derivative of the numerator is 2x plus cosine of x. The derivative of the denominator is 2x. Again, we have infinity over infinity. Okay, so we try to use the rules of the L'Hopital once more. Okay, so we get 2 plus 2 minus sine of x over 2. Okay, now we want to try to, so actually all those steps here are still in question because we haven't checked whether the last limit exists or not. Okay, now you see that this limit here, okay, does not exist. Okay, this means the limit is not, also the limit is not equal to plus infinity or minus infinity. Okay, so the limit simply does not exist, which tells you you cannot apply the rules of the L'Hopital. So no conclusion by the rules of the L'Hopital. Okay, so you must do it different. Okay, so this is quite subtle here. Okay, so you have to observe this point. Maybe in high school you haven't emphasized this. Okay. Now, indeed, if you look at this limit, what is the value of this limit? So you cannot prove, you cannot obtain this limit by the rules of the L'Hopital. You have to do it differently. So what is the value of this limit? What is the value? 1, right? Because so how can you handle this? Actually, you can use here the limit laws, but not the quotient rule. Okay, you write this first as 1 plus sine of x over x squared, and then you can use the rule that the limit of the sum is the sum of the limits, and the limit sine of x over x squared as x tends to infinity is by the squeezing theorem is equal to 0. Okay, so you have to do it here differently. So this is quite important to observe because from high school you might have got the impression that using the rules of the L'Hopital, okay, you can obtain whenever you encounter a situation like here, infinity over infinity, you can obtain the limit by using the rules of the L'Hopital. This is not necessarily true because you have to check the assumptions. Now, some more examples. Actually, one of the examples we have discussed previously in the assignments, namely sine of 2 to the nx minus 2 to the n sine of x over x squared. You see, this is much easier. So again, if x tends to 0, you have 0 over 0. You see, in this case, it's much easier to use the rules of the L'Hopital in order to figure out what is the limit, because the derivative of this one is the cosine 2 to the n x times 2 to the n minus the derivative of this one is 2 to the n cosine of x over 2x. So you see that if you plug in x is equal to 0, you get here 2 to the n minus 2 to the n, 0 over 0 once more. So this step is not certain yet. We have to apply the rules of the L'Hopital once more. And but if we do it once more, we get the limit x tends to 0. Now we have 4 to the n minus sine 2 to the nx minus or plus 2 to the n plus, yeah, sine of x half. Okay, and now you see, if you again use the limit laws, okay, indeed you get 0. Okay, so this means also that this step is now justified. And actually, you see more here. Okay, you see that if you replace here 2 to the n by an alpha, still true. Okay, you get still the same limit. But if you recall the method you have used in order to obtain this limit without using the L'Hopital, namely by essentially iterating the resulting recurrence, okay, you see that here for this example, you see that the rules of the L'Hopital are quite powerful tool, because if the alpha is 2 to the n, you can still handle the case differently. But for instance, if you have square root of 2, okay, it will be pretty hard to find a method which doesn't use the rules of the L'Hopital. Can you help me to wake up this guy? I'm a little bit worried. He looks like he fainted. Okay, so apart from those indeterminate forms we have seen so far, there are others, as you might have discussed in high school as well. So let's say other indeterminate forms. Okay, so for instance, you know that this situation, actually plus minus infinity. Okay, so this situation is also an indeterminate form. Okay, so if you encounter if you have two functions, f of x and g of x, the limits, and you consider the product of the two functions, the limit of f of x is equal to 0, the limit of g of x is equal to plus minus infinity. This is another indeterminate form. You know that infinity minus infinity, or minus infinity plus infinity, and so on, is also another indeterminate form. And you know that you have several indeterminate forms arising from such a limit. Okay, namely, because you can write this as the limits x tends to a e to the g of x times ln of f of x. Okay, and now you see you have the cases, because this can be infinity. Okay, so you have the case where g of x is 0 and this is equal to infinity. Okay, so there are two cases, 0 over 0. Okay, which is 0 means that here you have minus infinity, so you have minus infinity times 0. And the other case is infinity 0. Okay, so in this case, f of x tends to infinity. So the ln tends to infinity. You have again 0 times infinity. And then you have another case is where f of x is equal to 1, because then this is 0 and g of x plus minus infinity. So you have 1 to the plus minus infinity. You have to be careful, because sometimes students believe something like this here is equal to 1, or something like this here is also equal to 1. It's not true. Okay, because those are really indeterminate forms. Because one, you have to discover that this is an indeterminate form, and you write this here like this, then you see, just by looking at this one, okay, that those three cases relate to this situation here. Okay, now those three cases are actually just handled by using this idea here, so you can relate them to this case here. Okay, now this situation you can quite often relate it to 0 over 0 or infinity over infinity, just by writing the 0 as infinity over 1 over 0, or the infinity as 0 over 1 over infinity. Okay, so this case you can always relate to the case 0 over 0, infinity over infinity. And for this case here, you need it depends on the functions f of x and g of x. Okay, it can be different from situations, but sometimes the idea is if you have two fractions, okay, then you try to find a common denominator, or you factor out. You try to factor out some part, then you essentially end up with something like this and so on. Okay, so those cases are also all of those cases are indeterminate forms and can essentially be handled by the rules of the L'Hopital. So maybe let's look at some examples. So for instance, okay, so for instance, if you have this example here, you see as x tends to infinity, this tends to 0, and because the function a to the x is continuous, you get here 1. So this is 0, 0 times infinity. So you have here the indeterminate case, 0 times infinity. Okay, you should be aware that because you saw, for instance, 0 over 0 is an indeterminate form. Okay, sometimes, as you have seen in our assignment, 0 over 0, because of convenience, we define it as 1. Okay, now. Actually, what I mean by indeterminate forms is this is what you obtain if you would wrongly use the limit laws. Okay, we do not really obtain 0 over 0. Okay, because you are not allowed to use the limit laws. But we can think about this case as if you would wrongly use the limit laws. Okay, you get 0 over 0. This situation. Okay, this doesn't mean that 0 over 0 has a value. Doesn't mean this at all because we are looking at limits. And you saw that in different situations, it makes sense to define those indeterminate quantities, to give them a value, but it depends on the situation. For instance, as we have seen in the homework, if you use the sum notation for polynomials, it makes sense to say that 0 over 0 is equal to 1, which we frequently do in mathematics. Okay, so what I mean by indeterminate forms is if you wrongly use the limit laws, okay, you would get 0 times infinity, okay? But here you are not allowed to use the limit laws, okay? And the limit laws do not give you a conclusion. So I just give you some cases where the limit laws do not give a conclusion. And for those situations, we need different tools. Now, okay, so here we have 0. This is an indeterminate form of the forms infinity times 0, and as I said, you can relate this always to the situation. For instance, 0 over 0, so you can write this as a to the 1 over x minus 1 over 1 minus x. Okay, now you haven't done a lot, but because this is still an indeterminate form, but it's 0 over 0. So here we can use the rules of the L'Hopital. So we get that this is the limit. X tends to infinity. Now, if you take the derivative here, okay, the outer function is the exponential function. We know the derivative of the exponential function is this one, times the derivative of the inner function, which is minus 1 over x squared, over minus 1 over x squared, which is the derivative of this one. Okay, and now you see, okay, you can cancel out the bad guy. Okay, and what you get is the limit. Of course, you're not going to apply because you see, if you look at this here, you see what you get is again 0 over 0. Okay, but you are not going to apply here the rules of the L'Hopital once more. Okay, because then you will not get to a conclusion. Okay, so you cancel the bad guy, and then you are left with this limit here, which is much more easier. So now you can use the limit law, so you get ln of a. Okay. It's not a surprise, because if you look at this here, you can replace 1 over x by x, and here the infinity by 0. And what you have here is the derivative of the exponential function at 0, which indeed is ln of a. We have learned this already. So this already fits with what we have learned. Okay, so this is an example for the case infinity times 0, which can always be related to the case 0 over 0 or infinity over infinity. Now, let's look at some other examples. For instance, this one, the limit x tends to 1. Okay, so you see that also this is the indeterminate form here. Actually, this is a little bit different to the indeterminate forms we have discussed so far. Okay, because actually I should look here at the right and left hand limits. Only if I look at the right limit, this is really an indeterminate form, because this limit is not equal to infinity as x tends to 1. It doesn't exist, okay, because it depends how you approach. If you approach from the right, it's plus infinity. If you approach from the left, it's minus infinity. So strictly speaking, I should divide here into two cases, the right limit and left limit, that I can apply the rules of the L'Hopital as they are stated in the textbook. Okay, but because this is not infinity minus infinity, okay, because this limit does not exist. This limit does not exist either. It's not equal to infinity. Also not equal to minus infinity. But still, I can use here the L'Hopital. So you can think about this situation as infinity minus infinity. Okay, if you don't like it, you just look at the right-hand limit. Okay. Now the situation we encounter is really infinity minus infinity. Okay, and for such a situation, the normal, if you have fractions, differences of fractions, the normal idea is to choose a common denominator, which is quite natural, because if you do this, then you see that this is 0, and the denominator is 0 as well. So you have here x minus 1 minus ln of x. Okay, so now you have, what you have gained is, actually, computing the limit, you have gained nothing, but what you have gained is, this was infinity minus infinity, but this is 0 over 0, and here we can use the rules of the L'Hopital. So this must be equal to the limit x tends to 1 from the right. And if we take the derivative here, okay, what we get is 1 minus 1 over x over. And for taking the derivative here, we have to use the product rule. So we have 1 minus 1 over x plus ln of x. Okay, so you see that, again, 0 over 0. So we first make some simplification. Okay, so you can write this as the limit x tends to 1 from the right, x minus 1. You multiply everything by x, so you have x minus 1 over x minus 1 plus x ln x. Okay, but again, 0 over 0, so we use once more the rules of the L'Hopital. So we have limit x tends to 1 from the right. Now the enumerator is getting easy, 1. So now we certainly get a conclusion. Okay, over. And here we have 1 plus, and here we have to use the product rule. So we have another 1 plus ln of x. Okay, and now you see, okay, indeed you get a conclusion equal to 1/2. Okay, so actually, if I do not write here from the right, okay, it's not essential, okay, but you observed the first here, that the first limit, okay, is not of the form infinity minus infinity. Not strictly speaking, is not of the form, okay. But if you rewrite the first like this here, you get immediately 0 over 0. Then you have an indeterminate form, just strictly speaking. Okay, so this is another example. And as to the final case, for instance, we saw already this limit here. Okay, so actually here you have, if you try to use the limit laws, okay, here you have 1, here you have infinity, so you have 1 over infinity, the indeterminate form 1 over infinity. So this situation is different from this one and the previous one. But I have already explained how to handle this situation. So actually, what you do is you write e2d, then you have 1x ln 1 plus x. Now, e2d is a continuous function, so you can write the limit in the power. So you have e2d limit x tends to 0 from the right, ln of 1 plus x over x. Okay, and here you have now indeed 0 over 0. So you can use the rules of the L'Hopital in order to handle this limit here. But we already computed the similar limit. Okay, it's just shifted here. We computed the limits where you have ln x over x minus 1, and x tends to 1. It's just shifted. Okay, so we know already that this limit is equal to 0. So everything is equal to 1. Sorry. No, this limit was equal to 1, sorry. So it's equal to e, of course, because it should be we proved this result before, that e is equal to this limit here. and you actually previously we proved not only that the limit x tends to 0 from the right, but also from the left. Okay. Now you find this example, for instance, in the textbook. The reason why we have x, why the author writes x to 0 from the right is because if you come from the left, okay, if you consider the limit x tends to 0, actually you do not have 1 over infinity, okay, because if you have the limit x tends to 0, okay, this function has limit 1, that's correct, but this function, the limit of this function does not exist. Okay, but by looking at right-hand limit, left-hand limit, doing the same, okay, you get the conclusion. Okay, now similar. Let's maybe do one final example. For instance, the limit x tends to infinity. One plus 3 over x plus 5 over x squared to the x. Okay, so if we just simply want to use the limit laws, so if x tends to infinity, the base tends to 1, the exponent to infinity, so we have an indeterminate form of type 1 over infinity. Okay, so we will rewrite this as the limit x tends to infinity, and then use e to the x, and then ln 1 plus 3 over x plus 5 over x squared. Okay, now we can write the limit into the exponent because of continuous. So we have e to the limit x tends to infinity, x times ln 1 plus 3 over x plus 5 over x squared. Okay, now this you see corresponds to infinity times 0. Okay, so now we have transformed the original indeterminate form of type 1 over infinity to infinity times 0. Okay. Now I'm just considering this limit now. So this limit x tends to infinity. Okay, so we transform it now to 0 over 0, that we can apply the rules of the L'Hopital. Okay, over 1 over x. Okay, now this is really 0 over 0, so we apply the rules of the L'Hopital. Okay, so we have the limit x tends to infinity. First, the derivative of the numerator, which is 1 over 1 plus 3 over x plus 5 over x squared. So this is the derivative of the numerator times the inner derivative, which is equal to minus. So minus 3 over x squared, and the derivative of this one here, which is minus 10 over x to the cube, over, and the derivative now of this one, which is minus 1 over x squared. Okay, so you see that this here, now you can use limit laws, because this here tends to 1 in the limit, and if you look at this one, okay, as x tends to infinity, this tends to 3. Okay, so you see that overall what you get is that this is equal to e to the 3. Actually, it's not very surprising if you look at the original one, because as x tends to infinity, okay, this should be much smaller than this one. So this should dominate. So kind of you can forget about this. Okay, and we proved already that 1 plus 3 over x to the x as x tends to infinity is equal to e to the 3. Okay, so actually if I add here more terms with higher powers in the denominator, I will get the same result. They will not have any influence. Okay, so any questions to this? Now, as I told you, if we assume in the rules of the L'Hopital, in the assumptions, that the functions are not only differentiable, but also the derivative is continuous, okay, then the proof is easy. Now, if you think about functions with the properties, with the property that they are differentiable but not continuous, something which is not so easy to find. Okay, so want to have a function, you take the derivative exists, but it's not continuous. Okay, it's not so easy to find. Now, I know from experience in the Hoikau, there are sometimes questions like this. So maybe we should spend a little bit discussing something like this, because actually, if you want to find such a function, there is a result which tells you that such functions cannot behave too nasty. Okay, so if you look at the derivative, if the derivative is not continuous, okay, because we know if you have a function, okay, which is not continuous, for instance, this could mean that the function is jumps at some point, okay, has a jump continuity. Now there is a result which excludes this for derivatives, which is called sometimes called the intermediate value theorem for derivatives. So the following is true. Assume that f is differentiable on the interval AB. Okay, I explained already. If I write that f is differentiable on a closed interval, this means that the function is differentiable inside the interval in the usual sense. And for the two boundary points A and B, for A you choose the right hand derivative, and for B the left-hand derivative. Both exist. Okay. Now, so this means you have a derivative, okay, of the function on the whole interval AB. Okay. Now assume that C is a number in this interval here. Okay. So actually. This derivative here is the right-hand derivative at A, and this derivative is the left-hand derivative at B. Okay, and it might be, of course, that this number is larger than this one, but we assume, for the moment, we assume that this number is smaller than this one. Okay. So actually, we assume that the derivative of f at A is smaller than the derivative of f at B. Now. Or let's call this large L is maybe better. So there exists a C in AB such that the derivative of f at C is equal to L. Okay, so you have something like the mean value theorem. Okay, not the intermediate value theorem. If you remember, the intermediate value theorem tells you that for a continuous function on an interval AB, closed interval, okay, such a function takes on every value between FA and FB. So if you have a continuous function on interval AB, f of A, for instance, is smaller than f of B, and you choose L, which is between f of A and f of B, then there exists a C such that f of C is equal to L. Okay. This is for continuous functions, but here you have to look at the difference. The difference is, okay, f is differentiable, but the derivative might not be continuous. Still, because this function has the special property of being the derivative of some function, okay, this function also, it might not be continuous. It still satisfies the same conclusion as the intermediate value theorem. Now, this tells you, for instance, that if you look at, this is quite interesting, because this tells you that if you have something like this here, a function which jumps at 0, okay, this function cannot be the derivative of a function. Okay, the reason is because, okay, if this function is the derivative of a function, okay, you make this interval smaller, but then you can find a number which is not taken on by any C in the interval. Okay, so this kind of tells you that the derivative of a function, even so it might not be continuous, but it cannot jump. Okay, so it cannot look too ugly. Okay, in the sense that the discontinuities cannot look too ugly. Now, the reason we should maybe look at the proof of this, because in our Hoikau, okay, normally you have 110 minutes to solve the regular exercises, and then you get 2 more complicated exercises for which you just have 30 minutes. Now, sometimes those 2 more complicated exercises are really very complicated. Okay, and for instance, this was once an exercise. Prove this. Okay, I think this was much too complicated because this is actually the reason why this is complicated is because you are not trained proving such results. For a mathematician, for a mathematics student, it might be quite easy or not too complicated. But for someone who has no training in how to proving results, this is much too complicated. Sometimes those two additional exercises, but they do not count, so you can just get additional points, are very complicated. Sometimes not. Sometimes they're quite easy. So there are sometimes exercises where you just need the idea. Okay, it's a little bit similar to like those high school mathematics competitions. Okay, normally the exercises you get there, you need some idea, and if you have the idea, you can solve it. If you do not have the idea, you cannot solve it. But this is pretty different because here you, if you have a systematic training, okay, how to prove results, this should not be too complicated. But still, this is still, I think, it's still quite advanced to prove this here. Now, but actually, since this has appeared as one of those more complicated exercises, indeed we have the tools to prove it. Okay, you just have to figure out how to apply them. Now, here for this result, the reason why this is not so easy is because you need several ideas. Okay, and now the first idea. So maybe let's just spend 10 minutes to look into the proof. The first idea is that okay, you start with this case. Let's say smaller than 0. Yeah. You start with this case. You start considering this special case here. Okay. So first assume okay. I will explain in a minute why we start with this case. But if we have this special case, okay, where not only this is smaller than this, but this is smaller than 0 and this is larger than 0, okay. Now, if you try to depict the function, okay. So what do we know about the function? Okay, so we know the function. Actually, we know nothing about f of a and f of b. Okay, so f of a, of course, might be larger than f of b. Okay, so for instance, let's say this here is f of a, and this here is f of b. Okay. But what we know from this is here the slope. Okay, actually we just come from the right. Here the slope is negative, so the function will go down. Okay, and here the slope is positive, so the function will go up. Okay, locally, this is something we certainly know. Okay, so our function, because our original function f must be continuous because it's differentiable. Okay, so the function has to approach f of a like this and f of b like this. Okay. Now this means, okay, that if you look at the, this means that if you look at the minimum of our function f of x, maybe I write it. If you look at the minimum of the function of f of x, x in the interval ab, okay, our function f is continuous. So because of the extreme value theorem, there must exist an absolute minimum. Okay, if you look at this absolute minimum, okay, from this picture you can see this absolute minimum must certainly be smaller than both f of a and f of b. Okay. So once more, here you need the extreme value theorem. The extreme value theorem tells you this minimum exists. And because of this assumption here, it must be smaller than both f of a and f of b. But this clearly tells you that the minimum, the absolute minimum, is inside the interval ab. So it's also local. Okay. So this minimum here, call it. This is okay. So this minimum is taken on. Okay, I erase this here. So we know that the minimum of f of x is if x is in AB, because this function is continuous, exists by the extreme value theorem and is equal to, let's say, f of c. Okay. Now, from this here, okay, we see that C is not only absolute minimum, but also local. Okay, so C is a local minimum. Because it cannot happen at the boundary. Okay, and but this means that because our function is differentiable inside the interval, there is a minimum inside the interval. So by a Fermat's theorem, the derivative of f of C equal to 0. Okay. Now, why is this helpful? So actually, we have proved now that in this special case where the derivative of at A is smaller than 0, the derivative at B is larger than 0. Okay. We have proved that if you choose, because what we want to prove is that every value in between is taken on. Okay. We have proved that at least 0, which 0 is between those two, okay, is taken on by some C. Okay. So we have proved a very special case of the theorem. Okay. We have proved that if you look at the original theorem as I wrote it, if you have this additional assumption, if your L, okay, the value you are interested in is equal to 0, which certainly lies in this interval, okay, there exists a C such that the derivative of f is equal to this L, which is equal to 0. Okay, and so this is the first idea. Also, so for this already you need extreme value theorem, you need Fermat's theorem, and so on. You need to have this idea here. So this is the first idea. And now the second idea maybe is even more complicated. Namely, the second idea is to observe that this is enough because the general situation you can relate to this situation. Because if you have now in general a function f of x, okay, satisfying the assumptions of our properties, and you have L, you define a new function g of x as f of x minus Lx. Okay. Now you observe that this new function, okay, satisfies. Okay, if you look at the derivative at A, if you look at the derivative is the derivative of f minus L. Okay. Now, if you look at the derivative at A, okay, so you have because this L is between the derivative of f at A and the derivative of f at B. So this is smaller than 0, and if you look at the derivative at B, this is larger than 0. So this means for this function you can apply what we have just proved. Okay. So there must exist a C inside the interval AB such that the derivative of this function at C is equal to 0. But this means that the derivative of f at C is equal to L. And indeed, for every L, I have now found a C such that the derivative of f at C is equal to L. You see, I personally think this example was too complicated for the two more advanced exercises because you just have 30 minutes and you have another one to solve in the 30 minutes. So you have two exercises. This was just one of them. So this was certainly too complicated because this is more suitable for a mathematics student. So a mathematics student would maybe think it's not too complicated. But since you do not have a training improving, or we haven't emphasized training you improving theorems, you might find this not so easy. But still, this is quite interesting because it tells you something about the derivative of a given function, namely the derivative cannot jump. Okay, so this means that finding a function which has the property that the function is differentiable, but the derivative is not continuous, is not so easy. Okay, because those functions do not behave too badly. Okay, because of this theorem. At least they take on every value in between. Okay. Now, indeed, there are such functions. This is the last thing I want to say. So if you look at this function, okay, you can easily check on your own that the derivative exists, okay, everywhere. Also, so it's clear for if x is not equal to 0, it's clear that the derivative exists. but you easily check the derivative at x is equal to 0 also exists and is equal to 0. And then you write down the derivative completely, and you will observe the derivative is not continuous at 0. Okay, so this is a function which is differentiable at 0 but not continuous at 0. Okay, and indeed you see it's not so easy to find a more easier example like this because you see that this function, the behavior at 0 is quite special. It's not something like also if you look at you see that the discontinuity at 0 is quite special. It's not like the function is jumping or something, which is not possible by this theorem. Okay, because if we look at continuous functions, discontinuous functions at a point. Okay, for us possibilities are like you have an infinite discontinuity or you have a jump discontinuity. We have discussed this earlier. So earlier we have discussed jump discontinuities, infinite discontinuities, and removable discontinuities. But if you replace this function by this one, okay, then or this one, this function, the discontinuity of this function is pretty is different from the I don't know, the function is not defined here. So if you look at this function is continuous. But if x tends to 0, the way the limit does not exist of this function is quite special. And if you look at this function at the derivative, you see that the discontinuity at the discontinuity of the derivative at x is equal to 0 is not as simple, one of those simple types you might imagine, namely the function either tends to infinity. It tends to infinity at x is equal to 0, or it jumps at x is equal to 0. Nothing of those type. The limit just does not exist. So it's quite different from the simple types of discontinuity. And this is something which is expected by this theorem for the derivative of functions which cannot behave too badly. Okay, so any questions to this? Now, if not, then we go on Monday. Okay, that's it.